Hey all. So today we need to talk about projecting onto lines a little bit in preparation for projecting onto more serious things. Projecting onto lines is relatively straightforward. There's a little notational stuff that I'm going to kind of tweak that maybe isn't the same as what you've seen in Calc 3. If you didn't take Calc 3, this may be pretty new. Don't sweat it. It's not really very hard. The idea is pretty simple. So here's the idea. I've got a line W here, I've got a line here. Don't give it a name yet. And I've got a vector W. I'm just going to shoot my vector W off up here. So this is my vector W. Okay, and I've got my vector W there, and then what we're going to do is we're going to say, all right, this line, this blue line here, that's actually something about, oops, that's a terrible vector. Try that again. That's actually something about a vector here. I'm going to call this blue vector v. And then our line is really any scalar times v, right? So I'm looking at that line and I'm thinking that line is made of things that look like kv for some scalar. Okay. Hmm. Hopefully on board there. And my goal is going to be to break this vector w into two pieces. I'm going to break it into a green piece that runs along V here. That piece I'm going to call W parallel. Then I'm going to break it into a red piece that's going to go up here. That red piece is going to be perpendicular to V, and so that's going to be called W perpendicular. Now there's going to be three little facts that I need here. So let's write down our three little facts. So my three little facts are going to be that W parallel is in fact parallel to V, first fact. W perpendicular is going to be perpendicular to V. And third fact, W itself is made out of W parallel plus W perpendicular. Okay, let me fix my handwriting a little bit here. All right. So I'm hoping those are basically what I set up, right? I've got a blue vector V that runs out. If I span that thing, I make a line. I'm talking about another vector in space that I'm going to break off into a piece that's on the line and a piece that's perpendicular to the line. So I'm going to use my little facts here and I'm just going to write some stuff down. So here's the stuff I'm going to write down. I'm going to look at V dotted with W just because I basically don't know what else to do, but I know there's something about perpendicularity in here, and I know that dot products and perpendicularity play in a way that's fairly nice. So I'm going to look at kind of V uh, dotted with W. And I'm going to say, all right, well, I don't know what V dotted with W is, but I do know that it's V dotted with W parallel plus W perpendicular. And the only reason I know that is because my third fact here says that W is made out of those things. Now, I'm going to take just a second and let's talk about rewriting our first two facts. So the first fact is if W parallel is parallel to V, that means it's on the line. That means that I can rewrite W parallel as some constant times our vector V. That scalar, I don't know what it is yet. I'm not sure I'm going to be able to figure it out, but fuck it, we'll write it down. W perpendicular is perpendicular to V, which means something. That means that W perpendicular dotted with V ought to be 0. So I'm going to use those two facts right here. So I'm going to sub those two facts in here. And we're going to say that, all right, so now V dotted with W is going to be V dotted with some scalar times V. That's our W parallel again, plus W perpendicular. I can't do anything with that guy just yet. Now I'm going to distribute this dot product out. So I'm going to say this is V dotted with KV plus V dotted with W perpendicular. And this gives me a place where things are convenient. So I know that this dot product, because those two things are perpendicular, that dot product is 0. So this piece cancels, and I can say, all right, out of this, I can factor that scalar k. So I can get this as k times v dotted with v. Now, This gives me a nice, convenient way to write something down. This gives me a convenient way to write down that scalar k. So all this crap implies that that scalar k is actually equal to v dotted with w. Terrible handwriting, Joe. V dotted with w over v dotted with v. Keep in mind, the only reason I'm allowed to do this division is that v dotted with v is a scalar, right? I couldn't just divide by v and then divide by v. And some of you all might look at this and say, oh, we should just cancel a v. Can't do that because we're talking about vectors, right? So you can't divide by the vector v somehow. What we can do is we can divide by the scalar v dot v as long as that scalar is not zero. So as long as I'm actually trying to project onto a line and not just trying to project onto the origin itself, this is going to work for me. So I've got my scalar k. That lets me answer some questions, right? So that lets me answer the question of what is actually W parallel? Well, W parallel is actually just this scalar k times the vector v. So I'm going to write that as the vector v times this scalar here. That's the vector v dotted with w over v dot v. And I know I wrote this backwards just now. Trust me, there's a reason for that. It's a trick that will help us later. So, good with that? Okay. Next thing, where in the hell is w perpendicular here? So w perpendicular? Well, I don't actually know what w perpendicular is, but I think I can figure it out. So the way I think I can figure it out is I think I can figure out w perpendicular by saying, all right, I know that w is made out of w parallel plus w perpendicular, so I could subtract w parallel to the other side, right? So that would give me this other piece of information here, which is that w perpendicular is equal to w minus w parallel. So what I'm going to do is I'm going to rewrite my W perpendicular that way. I'm going to say it's whatever the original W was minus V times this scalar of V dotted with W over V dotted with V. Good on that? Okay. The reason that I wrote this in the funny way, and this is, so up till here, everything's been Calc 3. Like this is a standard thing I talk about in Calc 3. So you've seen this before, probably. Here in linear algebra, we're going to do one little thing different. And that little thing said, I'm going to rewrite this with transposes. So I'm kind of recalling a little fact. So I need to recall that V dotted with W is actually equal to V transpose times W. So with that in mind, I'm going to rewrite W parallel using that information. So I'm going to say W parallel is equal to V times, and then I'm going to put all this together. So I've got V transpose W, and then on the bottom there, I've got V transpose V. Are you on board with that? So if I rewrite this thing, I can rewrite this a little bit. And the rewrite I'm going to do is I'm going to take V and V transpose and put them over V transpose V and put a W out here. And this is a little weird. We should check that this is allowed. So I need to be sure that this top thing, that the dimensions make sense. Because I understood that V transpose W is going to give me a scalar. Knowing this is going to give me a scalar is maybe a little funny. So what I'm going to do here is I'm just going to grab this thing. And this is the beauty of this kind of one note thing. I'm just going to grab it and blow it up a little bit here. And let's check dimensions. So here are the dimensions. So V is some kind of vector, right? Like that's what I'm talking about. In my kind of picture up top, those are two vectors, right? In our case, we would say those are 2 by 1 vectors. I'm just going to write these down as n by 1. So I'm going to say I've got an n by 1 vector here. Once I've taken a transpose of that, that's a 1 by n vector there. W is an n by 1 vector. V is an n by 1 vector. And here I've got V transpose, which is a 1 by n vector. So on the top, the ones are going to tell me that I can do that, right? And the n's are going to tell me the size. So this top object is going to be an n by n matrix. This bottom object, as expected, right? The n's are going to match, which tells me I can do this, and I should get a 1 by 1. This thing down here is a scalar, right? I expected that because it's just a dot product that I wrote differently. On the top, I've got something different. I've got that n by n matrix. Now I can feed an n by 1 vector into an n by 1 matrix, and out of that, I'm going to get an n by 1 vector, right? That's these two n's are going to match. And so I can do this multiplication. So I'm going to end up, this whole thing here is going to be an n by 1 matrix. In other words, a vector, right? The dividing by the scalar doesn't change the fact that it's a vector. Be on board with that? So out of this, I got a vector, which is what I was expecting to get. So the reason for this whole business, and I'm going to kind of minimize this to get it out of my way. So we're just going to relegate that to the corner over there. So that's just my quick dimension check. Right, you guys don't need to do the dimension check. I just wanted to show you that it like is legit. I'm not playing funny business here. So what I want you to realize is that this thing here is a matrix, and this is the matrix that projects onto the line. So I'm going to call this P. You got to be a little careful. So, little careful now. Careful. P could be projection matrix. P could also be permutation matrix. So both of those are an option. In this lesson, I'm saying P is a projection matrix. You got to be careful with the book because he uses P for both things. You got to be careful with me because I use P for both things. If you're not sure whether something's supposed to be a projection or a permutation, ask. They're really different. Permutation matrices are generally invertible and have some specific properties. Projection matrices are generally not invertible. In fact, only the identity matrix is the invertible projection. Everything else is not invertible, right? When I smash a dimension, I'm 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 losing something, right? The null space isn't trivial. I can't undo it. There's a very weird fact that makes the identity matrix considerable as a projection. You can think about it as projecting onto the space as a whole. Not super relevant right now. Just be careful with these. They are different. So here I've got my projection matrix, right? That's made this way. So I want to demonstrate that this works a little bit. So I have two demonstration pieces for this working. So one of those demonstration pieces is this guy. So I'm gonna throw a link to this in both the video description and onto the Canvas shell, so you guys can see this. You can play with it if you want. So dragging the blue vector around changes our vector v, right? Dragging the end of the purple vector around changes our vector w. And here you can see I've got a green vector that's parallel to v. I've got a red vector here that's parallel to, or sorry, that's perpendicular to v. And you can see here how I made those. So there's nothing in here that's not what we just talked about. Feel free to look at it yourself and confirm that. But notice this, like the way this thing works. If I drag this W kind of pointed in the opposite direction, notice my little green vector is kind of anti-scaled to this vector V, right? Okay, so go in, play with this if you like. It's kind of cool. It's a fun little toy. The other thing we can do is we can make a little Desmos calculator, right? So I'm going to go ahead and put in a couple of vectors. So we'll put them in and then we'll check them with the picture. So I'm going to project onto the line 1, 2. So I'm going to make V1, 2 here. And then I'm going to make my vector W. I'm going to make it about that just to confirm. So That vector is relatively straightforward, right? So that vector is 0, 6. So I'm going to go in here and put in 0, 6. And then I punched in what I wanted there, and as it turns out, I don't actually want that. So here's what I want. I want to make my projection matrix. And Desmos doesn't let you do this. So I'm going to do, you can't just like type it in. So I'm going to do VV transpose divided by V transpose V. Okay, now that should be giving me a matrix. Why are you not giving me a matrix? Oh, that's so whiny. V transpose V is clearly a scalar, friends. Okay, so I'm going to skip ahead a lesson here and put it in here. So V transpose V's inverse. And then I'm going to project W here. So this whole beginning thing is my projection matrix. And then W here is my vector I'm projecting. So I've got 2.4 and 4.8. So that's going to be the parallel piece, right? So that's this green bit. So looks like over 2 and a bit, up 4 and a bit less than 5. Seems legit, right? 2.4, comma 4.8. Great. How am I going to get the red vector? Well, the red vector, I'm just going to take this whole thing, right? And we're going to do W minus W parallel, and that's going to give me this guy. And you might notice that this vector here, right, is in fact perpendicular to this vector V, right? So I'm feeling like all this is working. I hope you're feeling like all this is working. Thanks for the time this evening, or whenever you're watching this video. I will catch you guys later.